Today we're going to continue our exploration of fractional calculus, and we're going to be introducing a new type of function, in case you aren't already aware of it, that actually comes up a lot in fractional calculus, in particular fractional differential equations. So let's just give a brief overview of sort of where we are in this narrative. So one of the extensions that we have actually found useful for creating a lot of fractional differential and fractional integral operators is extending the factorial operator with the gamma function. And with this basic extension, we've actually come up with a few interesting properties. So the first is the alpha derivative of x to the n, i.e. the fractional power rule, is given by gamma of n plus 1 divided by gamma of n minus alpha plus 1 times x to the power of n minus alpha, which holds for alpha in the interval 0 to n plus 1. So that is what we call the fractional power rule. And the next thing that is actually sort of interesting is the fractional derivative of a constant c, which we can find to be equal to c divided by gamma of 1 minus alpha times 1 over x to the power of alpha. And again, similarly, this is sort of like a special case of the fractional power rule, which of course only holds for alpha in the interval 0 to 1. So you can only consider, for example, the half derivative, the 3/4 derivative of, for example, 6 or something like that. Now, this fractional constant rule has a special property that is worth mentioning. In particular, the limit as alpha approaches 1 from the left-hand side of this differential statement is actually equal to the Kronecker delta function. And in case you don't remember what that is, that's equal to positive infinity for x is equal to 0 and 0 otherwise. All right. And in particular, we found that the fractional derivative of an exponential via this extension is actually equal to a very interesting expression. So the alpha derivative of e to the lambda x, where lambda is a real number, is actually equal to lambda to the power of m times x to the m minus alpha. So it sort of has like a fractional power rule leading coefficient or leading term. Then it's times an infinite series, in particular the sum from k is equal to 0 to infinity of lambda x to the power of k all over gamma of k plus n minus alpha plus 1. Alright, so that is what we call the fractional exponential rule. Now, again, what is this n and what's its relationship to alpha? So this n is the integer part of alpha. So the floor of alpha is equal to m, and it satisfies the equation alpha is equal to n plus alpha minus n, obviously, but writing this sort of gives it a little new meaning. So this n is what we call the integer part, and this term here is what we refer to as the fractional part, right? Which typically only belongs to the interval 0 to 1, inclusive of the lower boundary, right? So that is just some of the basic properties that we've derived up to this point. Now one can ask, well, since exponentials play an important role in differential equations, and also it's going to play an important role in fractional differential equations, or FDEs, one could ask, is there anything special about this little infinite series hanging out at the end? And the answer is yes. Actually, this type of series actually has a name. These series are referred to as Mittag-Leffler functions, or it's a particular type of a Mittag-Leffler function. So Mittag-Leffler functions are actually a family of functions, and these functions have the following parametric form. So it typically has 2 parameters. There are some 3 and higher parameter versions of Mittag-Leffler functions, but 2 parameter versions are usually the most simplest to deal with. And this is defined to be equal to the sum from k is equal to 0 to infinity of x to the power of k divided by gamma of alpha k plus beta. So if we take this as a definition of the 2-parameter Mittag-Leffler function, then we can easily see that the fractional derivative via factorial gamma extensions of e to the lambda x is actually just equal to lambda to the power of n, x to the m minus alpha, times the Mittag-Leffler function. I'm just going to call it m. Some people use Greek letter e or just letter e, but I'm just going to use m with a fancy L sort of hanging onto it. That's just going to be Mittag-Leffler of 1 comma n minus alpha plus 1 of the function evaluated at lambda x. right? So therefore, the fractional derivative of an exponential function is precisely some polynomial multiple of a Mittag-Leffler function. So now that we have some connection between fractional derivatives and Mittag-Leffler functions, and Mittag-Leffler functions are sort of naturally connected to exponentials, and exponentials are, as we already know, a star of the differential operator d and also the integral operator I, then that sort of gives us reason to explore Mittag-Leffler functions with some algebraic curiosity. So what I want to do is just spend a couple moments talking about some of the properties and some of the connections to common functions you should already know with the Mittag-Leffler functions, and then we'll close off this little discussion of Mittag-Leffler with a couple other fractional differential expressions that you definitely should be aware of. So this is, again, the two-parameter Mittag-Leffler function, but the single parameter Mittag-Leffler function is also commonly explored in a lot of detail. So the single parameter Mittag-Leffler function is the same as the two parameter Mittag-Leffler function alpha beta with beta to be equal to 1. So Mittag-Leffler alpha 1, which is defined just to be equal to Mittag-Leffler alpha, is defined to be equal to, by definition, or as a corollary to the definition of the two-parameter version, the sum from k is equal to 0 to infinity of x to the power of k divided by gamma of alpha k plus beta is equal to 1, so that's going to be alpha k plus 1. So that is the single parameter Mittag-Leffler function. So let's just look at a couple special values of alpha and see if we recognize any of these functions from before. So the first example, let's look at Mittag-Leffler 0. So that's just going to be equal to what? So that's going to be the sum from k is equal to 0 to infinity of x to the power of k divided by gamma of 0k, right? And remember, gamma of 0k plus 1, let's not forget that lonely little 1 there, is going to be equal to what? So regardless of what k is, 0 times k is 0, so that's just going to be equal to gamma of 1, which is 0 factorial, which is going to be equal to 1. So the series just compresses down to the sum from k is equal to 0 to infinity of x to the power of k, which is a geometric series, which we know converges to 1 divided by 1 minus x, provided that the absolute value of x is in between 0 and 1. So that's the first Mittag-Leffler function, and we know how important geometric series are and their several applications. Let's look at Mittag-Leffler 1 of x. So that's going to be equal to what? So that's the sum from k is equal to 0 to infinity of x to the power of k of gamma of 1k plus 1. So that's just gamma of k plus 1, which we know is just k factorial. So we have the sum from k is equal to 0 to infinity of x to the k over k factorial, and that should be a very obvious series that is just e to the power of x, which we know is very, very important in several calculus applications. Let's also look at Mittag-Leffler 2. So what's that going to be? That's the sum from k is equal to 0 to infinity of x to k divided by gamma of 2k plus 1, which is the same thing as the sum from k is equal to 0 to infinity of x to the power of k divided by 2k the quantity factorial. Now on the surface this might not look obvious because notice the value of k here and the value of k there do not match. So what we can do is algebraically manipulate this value of x in order to get sort of a 2k in the exponent by doing a inverse algebraic relationship between, for example, squares and square roots. So we can write that instead as the sum from k is equal to 0 to infinity of the square root of x to the power of 2k divided by 2k factorial. And this should look very, very familiar. So this is just the even series with non-oscillating terms. So you should know that to be equal to the hyperbolic cosine function of the square root of x. Right, so that's Mittag-Leffler 2, and you can explore Mittag-Leffler 3, 4, 5, 6, and higher, and maybe you can see some other interesting functions that you've probably already encountered in the past. Another variation of Mittag-Leffler functions, not just the evaluations of Mittag-Leffler at various alpha values, but also the integrals and derivatives of Mittag-Leffler functions also generate other functions that we've actually seen before. So what I want to do is I'm going to go ahead and define I of Mittag-Leffler alpha of x to be equal to the integral from 0 to x of the alpha Mittag-Leffler function evaluated at minus t squared dt. Now it might not be obvious why I'm going to be evaluating the Mittag-Lefflers at minus t squared, but eventually it should become obvious why that is actually a good substitution for its interior parameter x. So what exactly is that? So for example, example 4, what would be the integral of Mittag-Leffler 0? So what is that going to be? So that's going to be the integral from 0 to x of Mittag-Leffler 0 evaluated at minus t squared dt. And that's going to be, as a power series, the integral from 0 to x of the sum from k is equal to 0 to infinity of what? So that's going to be equal to minus t squared to the power of k dt. And that's going to be equal to what? So let's decompose this into its alternating part and its non-alternating part. So that's going to be equal to the integral from 0 to x of the sum from k is equal to 0 to infinity of negative 1 to the power of k, and then let's do t to the 2k dt. And assuming that this series converges, the reversal of the infinite sum and the integral should be appropriate. And you can test the convergence of that if you wish. But notice the only part of this integral that depends on t is that t to the 2k term, right? So add 1 to that exponent, divide by that new exponent, and what is that going to give you? So it's going to give you the sum from k is equal to 0 to infinity of minus 1 to the power of k. Evaluate at x, that gives you x to the 2k plus 1 over 2k plus 1. Evaluate at 0 just gives you 0. So that's going to give us x to the 2k plus 1 all over 2k plus 1. Notice no factorials there. And notice that this series should look very, very familiar as well. Notice all the exponents and the bottoms are just odd terms, and that is, of course, the arctangent function. Right? So the integral of Mittag-Leffler 0 is the arctangent function. So let's look at another example. So that's Mittag-Leffler 0. What about Mittag-Leffler 1? Right? So example, what was that? It's example 5, right? So integral of Mittag-Leffler 1. So that's going to be equal to the integral from 0 to x of Mittag-Leffler 1 evaluated at minus t squared dt. So it's going to be equal to the integral from 0 to x of the sum from k is equal to 0 to infinity of minus t squared to the power of k all over k factorial. Remember, because it's gamma of k plus 1, which is just k factorial. Right. There's our dt there. And let's just rewrite this sum. So let's just move that out, and let's move that out as well. So that's going to give us the sum from k is equal to 0 to infinity of 1 over k factorial times the integral from 0 to x of minus t squared to the power of. Actually, you know what? What I want to do is actually keep that in its current form, because that's just precisely equal to something to the power of k over k factorial. That's just the e function, actually, right? So what we can do is just write that as 0 to the power of x times e to the minus t squared dt. And this integral actually should look very, very familiar, because that's very, very closely related to the error function, right? So what we can do is we can multiply top and bottom of this expression by the normalization constant, square root of pi over 2. And we can write that instead as the square root of pi over 2 times the integral from 0 to x of 2 divided by the square root of pi e to the minus t squared dt. And this precisely is the error function, right? So this is going to be the square root of pi over 2 times the error function of x. And that is the integral of Mittag-Leffler 1 of x. Right? Very famous function with several applications in statistics and probability theory, as you already know. But yeah, now that function sort of came into the picture. Now let's look at another interesting occurrence of other functions that we've encountered in single variable calculus, but let's look at the two-parameter version of the Mittag-Leffler function. In particular, Mittag-Leffler 1/2 and 1. So this is actually going to come in handy if you want to take, for example, half derivatives of things. Okay, so that's going to be equal to what? So that's going to be equal to the sum from k is equal to 0 to infinity of x to the power of k divided by gamma of 1/2 k plus 1. Now this is a little tricky to deal with, but this series should look very familiar to a function we've actually already explored before. Because, again, this is sort of like the single parameter Mittag-Leffler function, because, you know, if beta is equal to 1, this is just the one parameter version. But this function, this series, we should have encountered in single variable calculus, and if not, that's okay. So what I actually want to do is I want to evaluate this at ix instead of x. And that's going to give us the sum from k is equal to 0 to infinity of ik times x to the k all over gamma of 1/2 k plus 1. And this is the power series of a very famous function. That's just the Faddeev function, right? So if that's the Faddeev function, that means we know all of the identities associated to that Faddeev function. And that means what? That means the Mittag-Leffler 1/2 of Ix is just equal to the Fadiva function, which we should already know is expressible in terms of e to the minus x squared times the complementary error function EFRC of minus ix. All right. Now what we can do is we can just replace ix with x, and then similar things are going to happen in that exponent. So that means Mittag-Leffler 1/2 of x is just going to be equal to e to the x squared times EFRC of minus x. And we could leave it there, or we can get rid of that quadratic exponent by replacing x with the square root of x. So Mittag-Leffler 1/2 evaluated at square root of x is actually just going to be equal to e to the power of x times the complementary error function evaluated at negative square root of x. Right? So we have another connection to other functions via the Mittag-Leffler function, but now it's a multiplicative combination of the complementary error function, which has several applications in stats and probability, and a friendly little exponential term. Right? So those are some connections and properties associated to other functions for the Mittag-Leffler function. Now let us bring in a couple other properties that we are definitely going to be using once we start talking about fractional differential equations. In case you aren't already familiar with this from ordinary and also partial differential equations, the Laplace and also the Fourier transforms are very, very useful techniques in understanding and also finding solutions to linear differential equations and a couple nonlinear differential equations as well. So for example, the Laplace transform of some time variable function f of t can be just represented as this integral transform of that function, which is of course going to give you some function of the new frequency domain parameter omega. So one identity that you definitely should know, in case you are familiar with Laplace transforms of baby functions, is that the Laplace transform of a monomial term, t to the n, is actually equal to the gamma of n plus 1 divided by omega to the n plus 1. And of course that includes, for example, the square root of t, the cube root of t, t to the pi power, and stuff like that, because we, again, are extending factorials via gamma functions. Now let's see if we can get a nice expression for the Laplace transform of our Mittag-Leffler function, in particular the one parameter version, and you could of course get a two parameter version of this as well in case you're interested in. So what is the Laplace transform of the Mittag-Leffler function alpha evaluated at lambda t alpha? And again, you may wonder, well, why do we want to evaluate it at lambda t alpha? Eventually, once you start understanding the properties and the graphs and the convergence and the boundedness of the Mittag-Leffler functions, replacing it with these parameters definitely is going to be obvious eventually, right? Because this Laplace transform needs to converge. So therefore, we need to sort of implement some criteria on when this actually does converge and when it does not. All right. So if we just use the definition of the Mittag-Leffler function of alpha evaluated at this new parameter lambda t alpha, that's going to be what? So that's going to be the integral from 0 to infinity. Let's do our exponential term e to the minus t omega there, and then let's do our definition of Mittag-Leffler there. So the sum from k is equal to 0 to infinity of lambda to the power of k, t to the alpha k, all divided by gamma of alpha k plus 1. Now again, if you want to work with the two parameter version by replacing 1 with beta, that is perfectly fine, and you can get a similar result similar to the one that I'm about to obtain. Right. So what I want to do is I want to exchange everything that does not really have a t in it. So for example, this lambda k doesn't really depend on, well, it doesn't depend on t. This gamma alpha k plus 1 doesn't depend on t. The summation doesn't depend on t. So the only thing that I sort of need to keep in the integral is that term and that term, since those are with respect to t. So that's going to give us what? So that's going to be the sum from k is equal to 0 to infinity of lambda to the power of k all over gamma of alpha k plus 1. Times the integral from 0 to infinity of t to the alpha k, right? So that's this term hanging out there. And then what are we left with inside? So we still have this minus t omega term. So that's pretty much like the kernel of our transform, right? And that's pretty much what we're looking at there. Now, if you notice there that this is precisely equal to the Laplace transform of t to the alpha k, right? Because that's pretty much like our f of t in our general Laplace transform formula, because that's f of t, that's our kernel, and that's the integral transform of that particular function. So we actually already know how to take Laplace transforms of monomial terms. And alpha, again, doesn't have to be integer because we can extend that via gamma functions. So that means what? That means the Laplace transform of Mittag-Leffler alpha evaluated at lambda t to the power of alpha, that's going to be equal to what? That's going to be equal to the sum from k is equal to 0 to infinity of lambda to the power of k all over gamma alpha k plus 1 times, so what's the Laplace transform of t alpha k? So that's going to be equal to gamma of that exponent plus 1 divided by omega to that exponent plus 1. And if you notice something beautiful here, we have a couple cancellations, in particular those gamma alpha k plus 1s, and then we're going to be left with something very, very nice, in particular the sum from k is equal to 0 to infinity of lambda to the power of k all over omega to the power of alpha k plus 1. Right? And that's pretty nice. So now what I want to do is I want to evaluate this infinite series as much as possible, provided that the series actually does converge. So what I want to focus on is getting that exponent k on the top that's similar to that exponent k on the bottom. So I need to pull out an omega to get rid of that plus 1, and I need to decompose that alpha k into a product of exponents. So once I do that, what is that going to give me? So that's going to give me 1 divided by omega times the sum from k is equal to 0 to infinity of lambda divided by omega to the power of alpha, all to the power of k. Now notice that this is just something to the power of k from 0 to infinity, so that means this is just a geometric series, which converges as long as that term, absolute value, is between 0 and 1. So if that is the case, that means this is just going to be equal to 1 divided by omega times 1 over 1 minus that term, lambda over omega to the power of alpha. Now to get rid of this nasty little fraction, what I want to do is just multiply top and bottom by omega alpha just to get rid of that, and that's going to give us what? That's going to give us 1 divided by omega times omega to the power of alpha all over omega to the power of alpha minus lambda. And I can cancel some omegas there, so I'm just going to be left with omega to the power of alpha minus 1. So that's going to give us what? So that means the Laplace transform of the Mittag-Leffler function alpha evaluated at lambda t to the alpha is just going to be equal to omega to the alpha minus 1 all over omega alpha minus lambda. Isn't that nice? It's a nice little beautiful formula for the Mittag-Leffler function of m alpha. Evaluated that interior term, of course. Now, can you extend this to a more arbitrary term? Of course you can, and it's actually not hard, but this can be generalized to the following expression involving the two-parameter Mittag-Leffler function, but the Laplace transform of t to the beta minus 1 times Mittag-Leffler alpha beta of lambda t to the alpha. This is actually just going to be equal to omega alpha minus beta all over omega alpha minus lambda. Right? And notice the relationship between this and this. If you replace beta with 1, then 1 minus 1 is going to be 0. T to the 0 is going to be equal to 1, provided t is greater than 0. And of course, that just gives us the old version that we started with. Right? Now, what I want you to do, at least if you want to sort of think about what is the meaning of this and why do we want to multiply that expression by t, and sort of if you did study Laplace transform back in the realm of differential equations, remember that the Laplace transform of t to the n times f of t is actually related to the derivatives of f. Right? Because if you remember that this is equal to negative 1 to the power of n times the nth derivative of the Laplace transform of f, right? So the derivative of the Laplace transform is related to the Laplace transform of the product of a monomial term and that function, right? So now you can sort of see why that structure is actually very, very important. Now just a quick little analytical example, just in case you want to have some fun with algebraical calculations. Suppose I ask you to find what is the inverse Laplace transform of omega to the 5.2 all over omega to the power of 8 minus 4. The next very interesting and also very important relationship that I want to discuss in regards to Mittag-Leffler is one that can actually express one Mittag-Leffler function, the two-parameter version, as a linear combination of other Mittag-Leffler functions. And this is actually going to be very, very useful later. So this identity is going to start off like this. So I'm going to consider x times the Mittag-Leffler function of alpha. Alpha plus beta is the second parameter of x. And you may be wondering, okay, well, why am I multiplying by x? That should be obvious in a moment once I actually start doing this algebra out. So that's going to be equal to x times the sum from k is equal to 0 to infinity of x to the power of k divided by gamma of alpha k. So alpha is the first parameter, and then alpha plus beta is going to be the second parameter. Now what I want to do is focus on these first two terms and focus on the alpha that is in common between them, and then I can factor out. And I'm also going to distribute this x to that top exponent, and that's going to give me x to the k plus 1 on top. So that's going to give me what? The sum from k is equal to 0 to infinity of x to the power of k plus 1 all over gamma of alpha k plus 1 plus beta. And now you can sort of see why I wanted to introduce that x value there, because now we can use a nice little substitution without much trickery. So we're going to let L be equal to k plus 1. So obviously when k is equal to 0, that's going to generate L is equal to 1. So we can write this series instead as the sum from L is equal to 1 to infinity of x to the power of L divided by gamma of alpha L plus beta. Now this looks extremely close to a Mittag-Leffler function of parameters alpha beta, except we're missing the L is equal to 0 term. So what I want to do is I just want to introduce that term so I can write this as a Mittag-Leffler function. In particular, when L is equal to 0, that's going to give us x to the power of 0 all over gamma of. So when L is equal to 0, that's just going to give us gamma of beta, right? So that's going to be x to the 0 all over gamma beta minus x to the 0 all over gamma beta. So I'm just adding the same exact term, so I'm not really changing anything because that is just equal to 0. So now I can start to regroup things. So I can group these two terms together and write them as a series. So it's going to be the sum from L is equal to 0 to infinity of x to the power of L all over gamma of alpha L plus beta. That, as we know, is a Mittag-Leffler function, but we have this little 1 over gamma beta term just hanging out at the end, right? So again, that's going to be x times Mittag-Leffler alpha, alpha plus beta, of x, right? So from this, we can derive the following expression, because this is just Mittag-Leffler alpha beta. So that means what? So Mittag-Leffler alpha beta of x is just going to be equal to x times Mittag-Leffler alpha, alpha plus beta of x, plus 1 over gamma beta. Now that's a very cute relationship. So we can always relate alpha beta with alpha plus beta, where beta is just a number, typically taken to be some number between 0 to infinity. So this gives us a nice little relationship between two Mittag-Leffler functions, but you can actually get a relationship between three Mittag-Leffler functions by reoccurring this particular relation, because remember, if you replace beta with alpha plus beta, you can actually apply this relationship again and again and again and again. For example, if we want to replace alpha with alpha plus beta, that means alpha plus beta becomes alpha plus 2 beta, right? So that means Mittag-Leffler alpha beta can be expressed instead as x squared Mittag-Leffler alpha, alpha plus 2 beta of x, and then plus 1 over gamma of beta plus x over gamma beta plus alpha. That's pretty interesting. And we can continue this again. For example, Mittag-Leffler alpha beta x is equal to x cubed times Mittag-Leffler alpha, alpha plus 3 beta of x, plus 1 over gamma beta. Do you see the pattern? X over gamma beta plus alpha plus x squared over gamma plus beta plus 2 alpha. Now you can apply mathematical induction here if you want to, and we can get a nice, beautiful identity, and then we can sort of think about why do we care and why should we even be interested in this little identity. So Mittag-Leffler alpha beta of x can be represented as x to the power of n times Mittag-Leffler alpha, alpha plus n beta of x, plus the sum from k is equal to 0 to n minus 1 of x to the power of k divided by gamma of alpha k plus beta. So what do we have here? So notice that on the left-hand side, we have a Mittag-Leffler function, and over here, this is almost like a partial Mittag-Leffler function. And then we have just a Mittag-Leffler function that's sort of shifted in some sense times a monomial term. If you remember a very important property associated to the Laplace-transform of the nth derivative of a function, this identity should look very, very, very familiar to you. But I'll leave you that investigation on your own, but that's just a hint of where this might come in handy in the near future. So of course you can rearrange this to solve for this shifted version of that Mittag-Leffler function, and you can get the following identity, in particular Mittag-Leffler of alpha and alpha plus n beta of x is equal to 1 divided by x to the power of n of the standard Mittag-Leffler function alpha beta plus our partial Mittag-Leffler function k is equal to 0 to n minus 1 of x to the k minus n divided by gamma alpha k plus beta. Right? And again, that's just another way of rewriting one Mittag-Leffler function in terms of a series of other Mittag-Leffler functions, which again is going to be very, very important. Now that we have a few important properties associated to the Mittag-Leffler function, I just want to close off this conversation with a couple more fractional derivatives for you to sort of think about and their expressions in terms of Mittag-Leffler functions. So remember, if we extend the factorial via the gamma function, which we have been doing for a lot of these fractional extensions, then the fractional derivative of e to the lambda x can be represented as just lambda to the integer part of alpha times x to the power of n minus alpha times the Mittag-Leffler function of 1 and then n minus alpha plus 1 evaluated at x, right? And let's make that little m or our ml function a little bit more nicer, okay? So, as we should already know, the sine and cosine functions are very closely related to the exponential functions via complex numbers. For example, if I'm interested in the alpha derivative of the cosine of lambda x, what is that going to be equal to? So using that complex exponential connection between cosine and e, that's just going to be equal to the alpha derivative of 1/2 times e to the power of I minus lambda x plus e to the minus I lambda x. And this operator d alpha is linear, so it can distribute over those constants and also distribute over that sum as well. So that's going to give us 1/2 times the alpha derivative of e to the I lambda x, and then plus 1/2 times the alpha derivative of e to the minus I lambda x, right? Now we can employ our fractional derivative of e to the minus lambda x in terms of Mittag-Leffler functions, and we can obtain the following form. So it's going to be equal to 1/2 times I lambda to the power of m x m minus alpha times the Mittag-Leffler 1 and minus alpha plus 1 evaluated at I lambda x plus, that's going to be the first term, plus 1/2 times I lambda to the power of m, negative 1 to the power of m because we have a negative exponent there. And then again, that's going to be x to the m minus alpha, again of Mittag-Leffler of 1 n minus alpha plus 1, evaluated at minus I lambda x. We have a lot of common terms here, so we can factor them out. So we have the alpha derivative of cosine lambda x can be represented as 1/2 times I lambda m, x to the m minus alpha, so that's the common term, times Mittag-Leffler 1, m minus alpha plus 1 of I lambda x, and then plus negative 1 to the power of n, Mittag-Leffler 1, n minus alpha plus 1, and then we're going to be left with minus I lambda x. And if you want to explore Mittag-Leffler functions in more detail, maybe you want to consider the relationship between Mittag-Leffler 1 or Mittag-Leffler alpha beta I lambda x and Mittag-Leffler alpha beta minus I lambda x, because they definitely do share some symmetry, at least to some sense. So that is the fractional derivative of cosine. And similarly, you can find that the fractional derivative of sine of lambda x, so what is that going to be equal to? Do you know what that's going to be equal to? It's just a small change. We're going to definitely have an I in the bottom. In case you don't remember, that's part of the difference between the exponential representations of these two. Then we're going to have x to the m minus alpha. And then we're going to have, again, 1 m minus alpha plus 1, I lambda x. We're going to have a minus sign there, minus 1 to the power of n, Mittag-Leffler 1, m minus alpha plus 1, minus I lambda x. Right? So those are the fractional derivatives if we extend factorials with gamma functions. Now, all those are very, very wonderful and all. I just want to mention a very, very interesting identity that I think is very, very beautiful. What if somebody were to ask you, what is the fractional derivative of cosine lambda x minus I sine lambda x. Is the answer prettier or uglier than these expressions for sine and cosine? Actually, it's very easier because notice we do have some repetition in terms of both of these expressions, right? So if you actually focus on these two things, what are you going to get? So you will get minus I lambda to the power of m times x to the m minus alpha times Mittag-Leffler 1 m minus alpha plus 1 of minus I lambda x. It's actually a very, very simple function. So if anything, if you want to study some special Mittag-Leffler functions, you definitely should study Mittag-Leffler alpha beta of minus ix and Mittag-Leffler alpha beta of ix. And sort of see the relationship between those two functions. You're definitely going to see a lot of beautiful connections if you look at some of the geometrical notions of both of them, both in the real and also the complex plane. So those are just some very important properties associated to the Mittag-Leffler functions. There's so many more properties that I could talk about now, but our focus is of course going to be fractional calculus and the foundations of it, and sort of how Mittag-Leffler plays an important role in the solutions of several fractional differential equations, or FDEs. So until then, I hope you have a wonderful day. Take care.